Hi everybody. Today I thought we'd have a fresh look at the electronic DC load project. Some of you will recall. What I have been working on over the last few weeks is redesigning the printed circuit board for a new double-sided PCB, and finally got them made. So we now have a new printed circuit board which we're going to use today. And I also took the opportunity to add a few new features onto the project and make one or two minor changes and improvements to the circuit itself. So let's have a quick look at what we're going to do today. Here we now see the updates and changes we're going to make to the electronic DC load today. First of all, as I mentioned, we now have a new designed PCB, double-sided PCB, which has got a number of improvements on it. I've added a trim facility to adjust the 4.096 volt reference source that improves the calibration and accuracy of the unit. I've also now decided that we can store the user limit settings. That's the settings for the maximum current, the maximum power and the maximum temperature. We can store that now in EEPROM on the Arduino Nano, and that means that at switch on again those settings are retained. And the other option I've given here now is to have two different types of keypads. We can either now use a 5x4 matrix keypad that gives us 20 key functions, which helps us with all the features, or you can continue to use the existing 4x4 matrix keypad if you wish. So I'll give you both options for that. There's a new mode now on the unit. I've added the transient list mode in the transient settings, and I'll show you more of that in detail shortly. In order to add some of these new features, I've had to find some extra memory, so I've simplified the fan control part of the software. If you remember before, we were controlling the speed of the fan depending on different temperatures, which really is probably not necessary. So what I've done now is that when the temperature gets to a level where it needs the fan, we switch the fan on and we leave it on full. Number 7 here, Q6 to Q9, those transistors were the 2N2222A transistors, which we used as protection for the power MOSFETs. I found that they were quite hard to get, and the replacement for those now is the PN2222A, which is the equivalent. So I've decided to change those transistors for that type. The only difference is that the pin out connection is different. So the new PCB now takes account of that. So the layout on the PCB is for that type of transistor, for those from Q6 to Q9. A small change here, R39 has been changed from a 2.2 megohm resistor to a 1.08 megohm resistor, and R43 has been changed from a 180k resistor to a 270k resistor. And finally, we're going to go through a little procedure I've put together for doing calibration on this DC load. So they're the things we're going to go through today. Here we see the changes that I've made to the 4.096 volt reference source using the REF5040 IC U9 on our circuit. And we're now utilising pin 5, which is the trim facility, to accurately set that reference voltage. So I've added these three components here, two resistors and a little preset potentiometer there. So we take a 470k, go into the slider of the 10k preset, and we simply adjust that then until we accurately get 4.096 volts on the output. On the bottom end of that 10k preset, we've just got a little limiting resistor there of 1k going to ground. So we've just added those three components, and we'll see the adjustment of that during our calibration. Let's just have a look at the two matrix keyboard options that we can use on this update today. We can continue to use the 4x4 matrix keypad if you wish, and I will provide the Arduino code for that. Alternatively, we can use this new 5x4 matrix keypad. Now this gives us some extra ability to use a single button for all of the functions, rather than as before we had to press a button on the keypad and press the rotary encoder button at the same time to have some of the features. Now that will still apply if you continue to use the 4x4 matrix keypad, but if you choose to go for this keypad here, the 5x4 matrix, which now gives us 20 keys, then we have all the functions on this keypad. Now the only difference really is the layout of the connections going to the main printed circuit board there on this flexible cable there. You'll see on the original keypad here the cable comes out of the bottom of the keypad, whereas on the other one it comes out of the top. Also the 5x4 matrix keypad has an additional line for the extra row. Now the 5x4 matrix keypad here, you can see that some of the legend on the buttons is not relevant to our project. I mean, you can still use it as it is, and obviously you need to make a note of which button does which function, but what I thought we'd do is we'd create an overlay which we can stick on top of that keypad with all the correct functions on. So what I've done here is I've produced a overlay which I've printed on an inkjet printer on some glossy self-adhesive paper. It's got a backing on there which you can peel off, and then it'll stick onto the original keypad, and that will then overlay onto that original keypad and clearly indicate which functions we have. So we have the constant current, constant wattage, power, constant resistance, battery mode, transient mode. This button here is to set the user limits. We can now have a load on-off button on the main keypad, which we couldn't do before. We have an entry button, so as we enter information from the keypad in terms of the numbers, we can press the enter key to confirm that. We have the delete to delete any incorrect button presses that you make with the numbers, and I've indicated the decimal point there as well. So it makes it much neater in terms of the overall view of that keypad when you're using it for the DC load. And I'll give you a download for that with the template and the artwork for that, for printing that for yourself, and some details as well. Now I just want to have a quick look at the connections for these matrix keypads. First of all, we'll have a look at the 4x4 matrix keypad in terms of the row connections and the column connections there. Again, as I mentioned, the flexible cable is coming out of the bottom of the keypad, and the first 4 connections on that you'll see there are the rows, and that's rows 1, 2, 3 and 4, and the next 4 are the columns 1, 2, 3 and 4. And to the right of that you'll see that's the layout of the connections on the matrix keypad, the contact connections, and you'll see how those rows and columns are organized. Now the Arduino software, the code, we need to take account of those connections in the code, and I'll show you that in a moment. So the arrangement in terms of rows and columns and the numbering there, that will be reflected in how we organize our code for the keypad on the Arduino code. Well, let's have a look at the 5x4 matrix layout. Here we now have the 5x4 matrix keyboard layout showing the contact connections on the keypad. There you see the columns, there you see the rows, and also note the flexible cable is now coming from the top of the keypad on that left hand side, and this time the first 4 connections are not rows, they are actually columns 1, 2, 3 and 4, and then the next 5 connections are the rows, but they're counting from rows 5 to 1, which is the opposite way to what we saw on the 4x4 matrix keypad. So again, the arrangements here on this wiring is somewhat different to the 4x4 matrix keypad, and we need to take that into account when we look at the Arduino code for this project. Here we see the layout of the button connections for the pads, both for the columns and the rows, and you can clearly see how they're organized in terms of the numbering. So there's the 2 differences between the keypads. I'll give you this information as a download as well, which you can use on future projects as a reference. This now shows you the code used in the Arduino Nano for the 4x4 matrix keypad, and this is at the start of the program coding, and you'll see some reference to the rows and the columns, and in this case they're set to 4 and 4. And you'll also see the layout of the keypad, which is the mapping of the keypad which will be used, and that will reflect the keypad you see here on the right. And then the next two lines of the code there, that's where we specify the Arduino data pins used for the rows and the columns where the keypad is connected to. So those are the coding arrangements that we have for the 4x4 matrix keypad, which is fairly straightforward, and that's what we had on the previous versions of this project, so there's no change there. So let's have a look now at the 5x4 matrix coding. Here we now see the software for the 5x4 matrix keypad, so this is the setup for that. And the first change you'll notice there is we have the rows now set at 5, the column remains at 4. But the biggest change you can see is the mapping here for that keypad, and you'll notice the arrangement, how that mapping is shown. I've used letters A, B, C, D, E and F to represent some of these other function keys you see on the actual keypad itself. So the F1 button is represented by A on my mapping, F2 is B, the hash remains as hash and the star remains as star, but the up arrow is the C reference there, the down arrow is the D reference, the ESC button is the E reference, and the entry button there is the F reference on our keypad mapping. So that's changed there, and you'll also notice that that whole arrangement is sort of upside down compared to how we look at that keypad, and the main reason behind that is that we now have the cable coming out of the top rather than the bottom, so that's showing it the opposite way around there, the mapping on the software. And also the rows and the columns, the data pins for the Arduino, that's also now changed. So you can see here we've got rows going to data pins 9, 10, 11, 12 and 14. 14 is now actually the analog A0 pin, which was a free pin we left on our project for future upgrades, and I'm going to be using that for the 5th row. The columns are going to data pins 5, 6, 7 and 8. So as you can see, we've made some considerable changes here to the coding in the software to be able to use the 5x4 matrix keypad. And in view of that, I'll be giving you two versions of the software as downloads. One version which can run the 4x4 matrix keypad, and another version which can run the 5x4 matrix keypad. We'll just have a look at the new double-sided printed circuit board that I produced for this upgrade today of the DC load, and I'll just point out one or two features of this PCB. The output which is going to the load itself and the output terminal on the DC load there, I've got a large pad, solder pad there with quite a large hole in it, which will take a M3 nut and bolt there, so we'll bolt the positive connection to the load terminal at that point there. And I've got another large pad there which is the earth connection. In this case that is soldered on with a fair amount of solder there to keep the resistance low, and we can see that later when we look at the board with the wiring on. Now the other thing I'll point out is that these locations here of these little power resistors, those are the balancing resistors that we use for the 4 power MOSFETs. They're the 0.1 ohm resistors, and you'll note here that the track that connects them all at the other end is quite a large track to keep the resistance low as possible, and I've also put a similar track on the other side of the board as well, since this is a double-sided PCB. Now one important point if you do decide to build this project with this PCB is I would recommend that you solder all the surface mount ICs on the printed circuit board first before you mount any of the other components, and the reason behind that is it becomes quite difficult and awkward to solder them on once you have all the other components populated on the board. And this is particularly true for the two small SOT23 6-pin ICs there. You can see we've got one there which is U5, and we've got another one there which is U11. So just a point to bear in mind is solder the surface mount ICs on first. Make sure that you have them connected the correct way. I've actually put a little green dot on the printed circuit here to indicate pin 1. So make sure that you align the surface mount ICs correctly before you actually solder them onto the board. That's very important. It's easy mistake to make and have them the wrong way, and then you wonder later on what's wrong. So there we are. The board itself has got some nice screen printing on it, which it makes it easier to build, and you can relate all of the components on that board now with the reference numbers to the main schematic diagram that I'll provide as well. Here is a view of the reverse side of the PCB with the track on the other side, you see there, and there you'll see that we've got that thick track again, which is connecting the other end of those 0.1 ohm balancer resistors together for the power MOSFETs. Here we now see the new printed circuit board with all the components mounted. You can see there all the power components there bolted onto the heatsink. I'll just go from left to right. The first one there next to the fuse is the double shocky power diode there, the protection diode. The next four, there and there, are the 4 power MOSFETs. We then have the little power resistor there, the 0.1 ohm resistor, the sense resistor, and the final one there at the end is the temperature sensor, the LM35DT. Now these components are mounted onto the heatsink, and what I would recommend is that for the power MOSFETs and the power diode there and the temperature sensor, that you use some mica insulators which will insulate the power components from the heatsink, so it will isolate it from the heatsink. To get the best heat transfer, use some heatsink compound together with one of these small mica washers you see there, and you'll also need to use a insulator like that to insulate the nut and bolt as it's bolted onto the heatsink. Now I will give you a drilling template for these power components bolted to the heatsink there, just to make it easier for you. So I'll give that as a download which you can print off and mark on the heatsink the drill holes for all those components. I'll just point out a few other things on the printed circuit board. Firstly, the power resistors there, you see those 4 0.1 ohm resistors which are the balancing resistors for the power MOSFETs. What I've done there is, you can see I've stood them off slightly from the printed circuit board. So I've bent the leads around and they stood off from the board by about sort of 5mm or so. The other thing I'll point out is that on the printed circuit board itself you have a number of test points. So I've got a number of test pins scattered around the board where you can measure the voltage, such as the minus 2.5 volts, the minus 5 volts there. You've got the ground pin there. There is the plus 12 volt and the plus 5 volt. And in the middle of the board, somewhere about there, you've got the 4.096 volt reference. So you can test all of those voltages on those test pins in relation to ground, and the ground pin is there on the corner of the PCB. Now I've also mounted some small heat sinks with some heatsink compound on the 2 voltage regulator ICs there, as you can see, just to give some additional cooling for them. You can either do it the way I've shown you there, or you can bolt them to a metal chassis or whatever, but then you need to provide some insulation with a mica washer. But these are just freestanding. I didn't need a mica washer because they're just on their own individual heat sinks standing in free air. Now here you see all the presets on the board for the adjustment for calibration. The first one there is setting the voltage sense coming in, so that trims the voltage sense voltage. and we'll do that in calibration. You've got two pots next to each other there, which is setting the current of the DC load. So you've got a current null and you've got a current drive preset there, and then just above that you've got a preset there which is new now to the circuit, because we're trimming the 4.096 volt reference source to improve the accuracy. So that's what that preset is there. And then the last preset you can see over this side of the board is the one that we adjust the pulse width on the transient pulse mode. So they're the preset adjustments on the board itself. Now the connection to the keypad, you'll clearly see that I've got well, in this case there's 8 pins there which are used to connect to the matrix keypad. These would normally go to the 4x4 matrix keypad, and I'll show you in a moment the difference, how we connect the two keypads, whichever option you choose. I just quickly want to indicate the orientation of the Arduino Nano when it's plugged in onto the board. Make sure you have it in that orientation with the little USB socket there going towards where the rotary encoder connection is and the transistor for the fan. The first keypad option is the 4x4 matrix keypad, which we've used previously on this project. That's the one there, and we're simply going to connect the little flexible cable into the header pins there you can see on the printed circuit board. So you've got 8 pins there, and the connector just plugs into those 8 pins in that direction. So the cable is coming from the bottom of the keypad. So that's the 4x4 matrix keypad, so there's no change there to what we had previously. Now if you wanted to use the 5x4 matrix keypad, then we need an extra connection for the 5th row, and let me just show you how we achieve that. Now in order to use the 5x4 matrix keypad, we need an extra connection for the 5th row, as I mentioned. I've just removed the Arduino Nano and just pull the Darlington transistor up so we can see the connection on the board, and just there near the edge connector for the Arduino Nano you'll see that there's a pin connection on the board there labelled A0, and also it's labelled J14, and that's the connection we're going to use for the 5th row on the keypad. So we simply take a wire from that, sort of a stiff wire. I've used some solid wire, and we're taking it to a pin which will plug into the cable, the ribbon flexible cable on the keypad, and I've taken it to one of these pins, which is a right angled pin, which is similar to the inline header pins there, but this one is bent at a right angle, so we can then solder the wire onto that, and then that can be positioned next to the other 8 pins, and then in that case we've got 9 connections now which will be going to the keypad. So that's how we get the extra connection for the 5th row of the keypad. So let me just show you with the keypad connection. Now when using the 5x4 matrix keypad, the way it's connected onto the printed circuit board is with the flexible cable coming out of the top of the keypad, as you see there, and then that is bent down and plugged onto the board, and the last pin on the right here is then what's going to go to the extra connection that I just showed you, which goes to the A0 or J14 connection on the printed circuit board. So the best thing to do is connect the last pin in, I'll just zoom in and have a look at that. So there we see the pin connection there going to the last pin there on the flexible cable, and then the other 8 connections on that cable then simply will plug in to the main header on the PCB. And there we are, that's the cable. I have made a little information sheet here showing the details of wiring the 5x4 matrix keypad and showing the fifth row how that's connected to the A0 output from the PCB, and I'll make this available as a download so you can use it as a reference. So there we now see the 5x4 matrix keypad plugged into the PCB with the last connection on the right hand side there, which is going to the AO pin on the printed circuit board via the small wire. I've made a little table here showing the key button functions on both the 5x4 and the 4x4 matrix keypads, and I'll make this chart available to you as a download so you have it then as a reference. I just want to point out a little issue I found when I was ordering these 2-pin connector plugs here, the JST 2-pin plugs on eBay. I've ordered it from a number of suppliers, and in some cases the red and black wires are reversed. So sometimes you get it like you see here on the one there, or sometimes you get it as you see on the top one there. Now you need to be careful when you use them on this DC load, because if you look at the DC input there, you see we've got a positive and negative mark there on the socket. The opening of the socket usually goes in towards the center of the board, and that means you need to be careful that when you have your connector plugged in, the positive is always going to that point there, the bottom one in this case. So the correct one to use would be the one you see here at the top, and when that's plugged into the socket and the socket's in the board, then that is the way that the red and black wires should go, positive and negative. If you were to use the other one, the other lead that you can also get on eBay, then you either have to swap them round, or alternatively what you could do is you could put the little 2-pin socket in reverse so the opening goes on the outside. So you could simply reverse that and then put it in that way. So that, just be careful when you're doing that, and the same applies for the voltage sense input as well. For some reason sellers on eBay, they're selling two different types, so just make sure that the positive and negative are going to the right connections on the PCB. Here we have the DC load now all connected up and powered up. I've got the display connected, the keypad, the rotary encoder. I also put in the load on off button, although we do have the load on off facility here on the keypad as well. And I've got the load connected at the moment to this DC power supply, and the sense wires, the voltage sense wires, are also going to the DC power supply. The fluke meter we have there is in series with the load, so that's going to monitor the current when we activate the load on, so we can adjust that as we calibrate. Now the first thing I'm going to do is adjust the voltage sense preset, that's RV2, until we get the same voltage on the display here, on the DC load display, that we see on the meter. That's the 5 volts. So let me adjust that and see if I can get it as close as I can to the 5 volts that we see there on the meter. I think that's pretty close. So the display is now showing 5.002. It's as close as we can probably get to what we see on the meter. So that's the voltage sense circuit now set. The next thing we're going to do is set the voltage reference on the board. That's the 4.096 volts, and to do that I'm going to connect the meter here to that reference pin which we have here on the board. So let me just do that. Right, we now have the meter connected to the 4.096 volt reference pin, and we're just monitoring that. You can see at the moment it's reading 4.1004. So I'm going to adjust that with the reference preset, which is just there, and get 4.096 volts on the meter. It's pretty close, just a touch up. I think that's quite close there. I'm going to leave it there. So that's 4.0967. I think that's, maybe just trim a little bit more maybe, and we're going to leave it there. So that's now set. The next thing we're going to do is adjust the current calibration. That's the current cal and the current null presets. What I've done is I've connected the voltmeter here back to the voltage coming out of the DC power supply, so that's monitoring what's going into the sense input circuit there. That's the 5 volts in this case. And I've got the fluke meter there in series with the load, so that's monitoring the current. So the first thing we're going to do is we're going to set the current on the DC load to 3 amps. And enter that, so that's at 3 amps. And then when I switch the load on, we're then going to adjust RV4, that's the calibration preset for the current, until we get a 3 amp reading on the meter there, and we should get something as close as that on the display here on the DC load. So let's switch the load on. So we're now drawing 3 amps, but the fluke is only showing 2.97. So although we've got it set at 3 amps, the calibration is slightly out. So we're going to adjust now RV4 until we get 3 amps on the fluke. Just about there. So we're showing 3 amps there on the fluke. It's actually showing 3.007 amp on the DC load, but maybe that's within the tolerance. We'll rely on the fluke for the moment. And the next thing we're going to do is we're going to switch the load off. We're now going to set the current to 0.1 of an amp, that's 100 milliamps. And this time when we switch the load on, I'm going to adjust the current null preset till we get the correct reading of 100 milliamps, and that preset is RV3. So let me switch the load on and let me adjust RV3 until we can see the 100 milliamps on the meter, just slightly high on the fluke. About there. So we're drawing 100 milliamps. You can see there on the fluke. It's actually showing us 0.095 on the DC load, so it's showing us 95 milliamps. So a slight error there. Now we're going to switch the load off again. We're going to now go back and set the load to 3 amps. And we're going to switch the load back on again and go back and, if need be, adjust RV4 so we get 3 amps. So it just needs a slight trim. There we are. Switch the load off. And then we're going to set it once more to 0.1 of an amp, that's the 100 milliamps. And we're going to switch the load on one more time, and if need be adjust the current null preset RV3 for the 100 milliamp. But as you can see there, we don't need to do that, it's okay. So that now should be the current calibration set, and just to see how accurate it is, I'm going to just advance the load using the rotary encoder. I'm going to take it up to 500 milliamps, and you see there what we've got on the fluke is 499 milliamps, which is close enough. Here we've got on the DC load 495. Let me go up now to 1 amp, and the fluke is showing us 0.998. It was hovering there between 0.998 and 0.999 milliamps. That's close enough, as we have there on the DC load. Let's now go up to 2 amps. It's showing us 1.998 amp on the fluke, and it's showing us 2.001 on the DC load. So let's go up to 3 amps. It's showing us 2.999 on the fluke. You can just maybe just trim the current calibration preset one last time, just to increase it slightly. There we go. So that should be okay now. I will provide you with the details of calibration. It's a case of going backwards and forwards a few times with those two presets on a high current setting and then a low current setting. But I'll give you that detail as a download you can download and do yourself. I'll now just demonstrate some of the new features we've added to the DC load. And the first one is the user setup limits. So if I press the limits button on the keypad there, it goes to user setup, and the first thing it allows you to do is set the maximum current. So let's say we set that to 4 amps. So we type in 4. This only takes whole numbers for these settings, so you can't do decimal places. So you set it to 4 amps in this case. Press enter. We can then set the maximum power. So let's say we set the maximum power to 80 watts. That's an example. Press enter. And then you can set the maximum current limit. So once it reaches that, the temperature on the heatsink, it will cut out. So let's set the maximum temperature to say 60 degrees C. So we press enter. That is now set and saved in EEPROM in the Arduino. Now that means that if you switch the load off and then on again, it should remember those settings. So I'm going to unplug the DC load, remove the power, and then plug it back in again. And what you'll see when it goes back in is you'll get the intro screen, and then shortly after that it'll show you the limits of the settings. There you see 4 amp, 80 and 60. So it remembered what we set when we powered up again. So those are user-defined settings that you can do. Now I just quickly want to show you what happens if you use a brand new Arduino Nano and you program it with the software for the first time. The EEPROM memory in the Nano has not been used before, and therefore it's set at its default setting of FF. So that means that all of the limits will be set at 255. So what we have in the software is it recognizes that problem. So when you initially switch on, it will prompt you to enter the user limit. So let me just switch on and show you that effect. Comes up with the intro screen. Then you see the limits all set there 255, and it immediately goes to the user setup. So it doesn't allow you to go to the other modes until you set up the limits. So let us now set up the limits. Let's set the current limit to 4 amps. Let's set the power limit, say, to 90 watt. And let's set the temperature limit to 70 degrees C. And I press enter for the last time. And then it stores that information and goes to the normal screen for constant current. Now if we switch off the unit, and the next time we switch on, it'll remember those user settings. So let's see. Comes up with the instructions, and it shows you there the user settings, and then it goes on to the normal functions of the DC load. So a little change I made to the software there to recognise that fact if it's a new Arduino Nano that's not been programmed before and the EEPROM is all set at FF, so that's what you'll see. Now the other feature that we have is in the transient mode, so I'm going to press the transient button, and you'll see here on the display now we have an extra feature, which is the list mode, transient list. If I now press 4 on the keypad to select transient list, this now allows us to enter between 2 and 10 different sequences of current and time, and then once you've done that it then will loop through those settings. So let me choose, just for this example, I want to say 3, so type in 3, it shows on the display, and then type enter. So we're going to have 3 different current and time settings. It comes up on the display, it says the set current 1, so we're going to set the first current to say 1 amp and enter. We're going to set the time, say, to 3000 milliseconds, that's 3 seconds, enter. It then goes to set current 2. We go to now set it at 2 amps, enter. We now can set the time, say, to 2000 milliseconds, that's 2 seconds, enter. And then it goes on to the third, set the third current, so let's now set it at 0.5 of an amp, enter, and we're going to set the time to 5000 milliseconds, that's 5 seconds. This time when I press the enter, it goes to the transient mode display. You'll see there, the bottom right hand corner, you've got TL, it's the transient list mode, and those currents now are set in memory and those times are set in memory. When I now switch the load on, it will sequence through those one after the other, then go back to the start again, so it's rotating round. So let me switch the load on. So you see the first current for 3 seconds is 1 amp, then goes to 2 amps for 2 seconds, then to half an amp for 5 seconds. It'll now go back to 1 amp for 3 seconds. So it's rotating around that loop of settings that we've set in the list. And that can be quite a useful feature for testing power supplies and other circuits as well. So that's a nice addition we've added to the transient mode menu. We now switch off. If I switch off, the load stops, the loop stops. I can switch back on again and it will go through that loop again. So switch off. If you go back to the transient button, if you select transient list again or you select any of the other transient modes, it resets everything, so you have to input your current and time. So that's the new feature in the transient mode. The last thing I want to cover regarding setup is adjusting the little preset there which adjusts the pulse width for the transient pulse mode. And a simple way of doing that is using a multimeter on the ohms range, but make sure that the DC load is switched off and disconnected from any power. And then if you identify the resistor R28, which is just there, and if you go on to the end of that resistor nearest to the capacitor and the preset and measure that resistance to ground, you'll see I've got the other end of the meter there connected to ground, so I'm just going to measure that resistance at that point. It's reading 231k, and adjust the preset now for a reading of 250k. Just around about there. So when you've got about 250k, then that is set correctly. Now another way of doing it is using an oscilloscope, and I'll show you that next time. Well, I hope you found that update on the electronic DC load of interest. With regard to the new double-sided PCB here, I have had a few made, so I'll make them available on eBay if anybody is interested in purchasing one of these, and I'll put the eBay link down below as well. But you can simply search on eBay for Scullcom and you'll find any of my PCBs there. With regard to all the information for this update, I'll give that down below as some download links, so I'll provide you with both versions of software, either for the 5x4 or the 4x4 matrix keypads. And in addition to that, I'll provide you with a zip file with all of the other information in, which includes the full schematic and also any of the information sheets I've discussed today. Well, I'm going to leave the project today. I may do a quick video later showing you how I've integrated that new PCB into my project box, which we used earlier. But for the time being, I think that's for another day. So thanks for watching. If you found this of interest, please give me a big thumbs up and subscribe, and I'll see you all again soon.